Hello, thank you for attending our online seminar for improving EV charging uptime with surge protection. I'm Mark Hendricks with Dane Inc. Welcome to our session. This is available for 1 hour of contact, which is a tenth of an hour of learning credit. Thank you. Quick introduction to myself. Mark Hendricks with Dane Inc. The seminar will look at lightning protection standards and how surge protection, air terminals, down conductors, grounding, and bonding are selected. And in particular, we're looking at the draft standards like IEEE C62 that cover suggested surge protection applications, along with the lightning standards, IEC and NFPA that cover the lightning environment and what it takes to actually improve product performance, EV charging uptime, and how to get the most out of your EV charging asset. And a quick reminder, here is the file and license number for our continuing education. We'll be very pleased to be offering the attendees certificates upon completion of the attendance of this session. Dane is a family-owned company, over 100 years in this business, doing surge protection devices since 1950. We've been at this core market space, surge protection, lightning protection, and grounding for as our core business. We're very active globally. I'm Mark Hendricks with the Dane USA subsidiary, and welcome to our session. So lightning, I'd like to start with this photograph because it's got a lot going on. And this is a particular type, like considered a downstroke from cloud to ground. There's many flavors of lightning and who's who in the zoo, including the severity of the stroke and the charge content. The Ka is a kiloamp reference to the measured kiloamp of the actual charge moving through the atmosphere. Charge in motion makes amps, kiloamps. And with that sort of mathematical approach, you're able to evaluate lightning in the particular function of step leader attachment. And here in this photograph, there's just a lot going on, but you can see that there's some wispy tendrils of lightning that did not attach to the main channel. Those step leaders are essentially a calculated electric field distance. And so all other things being equal, as this charge is about to attach, the step leader is a basic what's called a attachment point, and that radius of an electric field is influenced into the space around these trees, and everything in that environment is under that electric field influence, and the tendrils are provoked, trying to become the main channel that attaches, and you get that step leader attachment, you get the main channel of lightning coursing through the body of the stroke. So there's a lot going on, and the science of lightning protection, really helps understand what's happening in the environment. The pillars of protection are a basic way for us to look at any structure, any environment, and evaluate, are there air terminals? Is the air termination system, is the Franklin rod in place with a down conductor taking the lightning energy into the earth termination system? And in our electrical world, there's a lot to pay attention to in separation distance and lightning protection bonding and electrical equipotential bonding. And so these sort of 5 things become the areas of improvement to go from a high risk incident to a very low risk environment. And I like to use this as an overlay because it tells you a lot about any particular environment. And you can overlay this, for instance, to a data center or a hospital operating room where you have layers of protection. So the lightning protection zone on the outside of a structure is considered at risk. If you're below the coverage of the air terminals, you're in the lightning protection zone B, which is protected, outdoors protected, but you now have the virtue of not being subject to direct lightning strike attachment from that rolling sphere charge ball that could provoke a tendril, and you could become the attachment point, like this light pole off to the right hand side, where it's under its own protection from the virtue of the light mast itself. So you have the air terminals, you have a down conductor systems bringing lightning energy into the earth. You have equipotential bonding everywhere you can, where the structures and the framework between the grounding members and columns embedded in concrete, in the wall, in the floor. And then you have surge protection, here depicted with the conveniently with red and yellow for power systems and information technology systems, things like data communication. And as you move into the core of the operating room or the data center or the charge station equipment, you become more and more protected with lightning protection zones by virtue of grounding and surge protection. So you can overlay a sketch like this even to something as simple as equipment that's mounted on the wall in a garage to charge your electric vehicle. So you'll have things like the electric panel, the service branch panel. You'll have bonding between the earthing and bonding of that electrical service. You'll have surge protection devices for the power, the red type products. You'll have surge protection on data, and you'll have equipotential bonding bars in that electrical service. But notice that the bonding and the connections to something like the apparatus that might hang on the wall. And so this is all part of taking the larger pillars of lightning protection and how do we apply that into charge station, into charge equipment. This is a couple simple diagrams. That this is the sketch that comes directly from the IEEE C62 standard that gives us some pretty good guidance on the application of surge protection for below 1,000-volt type power systems. And so you have the selection of surge protection to fit the AC power. And then here's just some of the common components. And now you take that picture in your mind and you have the charge apparatus, you have the actual equipment that you're protecting. For instance, what's the most important thing in that electrical circuit is probably the electric vehicle itself. So it's important to keep that all in your mind's eye picture. What is it you're trying to protect? I like to call that the victim of lightning. So we would want to make sure that our measures of protection are covering the risk of the application. Here's a really common type of a charge pole that you'll see in the industry. And there's a few things to notice about the way it's actually installed versus the sketch to the right, which is, okay, what are the things to look for? So at this particular charge pole, it's going to be very difficult to validate that it has grounding applied directly at that charge electrical console right here that's out on the curb. Simply the simple fact that the curb hasn't been all chopped up tells me that it probably doesn't have a real purpose ground rod attached directly at the charge pile. Likewise, it's difficult to know if there's surge protection devices inside the pole, or is it back at the feeder box, transformer or a switchgear that actually is feeding this electrical charge pile that's at a hotel, for instance. So when you see a picture, you know, in your mind's eye, you want to overlay the pillars of protection. Is this actually been protected? So these are the topics we'll be looking into in some pretty good detail. The lightning standards to talk about come directly from NFPA 780 and the IEC 62305 type standards. And basically, they're fairly well harmonized with a few key differences. The NFPA 780 adheres to several UL protection products. It defines the use and gives you direction to use these types of products. 1449 for surge protection devices, UL 467 for data protection devices. And the Lightning standard gives you a really good guidance on the ratings of the product, the safety levels, the protection levels. And so it gives you some guidance that helps you select the right types of products and the right types of measures to reduce risk. The IEC standards likewise refer to products and the actual physical lightning protection materials and the surge protection type products. And I'd like to think that the standards are a lot closer coordinated. There's a few key differences between IEC and 62305 and the NFPA 780 standards. And I think that the key area to notice as a difference is the actual description and definitions of lightning intensity waveforms. There's a lot more method of calculation in the IEC standard, the way it applies protection to an application. You evaluate your risk. You apply measures to reduce risk. Based on your level of risk, you have more or less calculation variables. And NFPA 780 uses much more of an example type application. I think that's the difference in the philosophies. Here's just a quick list of some of the things that are noticeable differences in the way the standards are applied and the way they read, but they're very well harmonized as well. I don't want to take away the fact that the NFPA 780 and the IEC standards are for human safety and fire protection. And so they're use very much the same principles of lightning. The NFPA 780 has an example-based method called air terminal placement, but it also uses that same function of the rolling sphere that we briefly discussed, where the final step leader distance determines the sphere that you roll over an object, and all the nooks and crannies that get touched by the sphere are likely targets where that air terminal can attach. And you want to lift that protection up with air terminals. This is the Franklin rod. And then there's also a look at the protection angle, where it's much like you see in things like electrical switchgear yards, where there might be a large mast that is isolated from the other equipment and grounded into the same earthing system, but the lightning does not go through the equipment. You're putting the lightning into a mast, sort of isolating from the other equipment. And that is in contrast to what's very common in the NFPA 780. It uses UL 96 type products, and it's much about bonding and keeping everything at the same electrical potential, which is a very good way to control touch step voltage. It's very safe and effective. A lot of times visually it looks a lot like this type of, you'll see it a lot where the air terminal is attached and bonded to metal framework and fan vents, maybe things like air chillers that are up on the roof of a structure. And so you'll see things like these air terminals on the structure bonded to the framework. And this might be over the top. You can picture this in a charging station type environment where it's around the buildings adjacent to the charge station, the hotels, the convenience stores, the things where a charging station is going to be. And you'll notice that the lightning is subject to be injected directly into the frame. And then some of that lightning current finds its way directly into the electrical systems within a structure. So in the world of lightning protection, UL offers a complete third-party inspection type service where they'll review your standard to NFPA 780 or to government military standards, or they'll review your site to the IEC methods. And it gives you a third-party master label that is usually a certificate type that's good for 2 years that shows that your system has been designed and meets the and installed and inspected to meet the intent of these practical lightning inspection standards. The IEC standard is broken into four sections. It's the principles of lightning protection, risk analysis, lightning protection for structures, the actual external lightning rods and down conductors, and surge protection as the fourth section of the standard. So there's four sections, and each one dealing with key areas. And the area that it really always starts with is section 2, which is lightning risk evaluation. So in the process flow for lightning protection of any structure, charge station, hospital, you evaluate your risk. Is it a charge station where it's highly exposed? Is it subject that there's a lot of humans present? There's actually a high risk for human safety. You're near things that could be explosive. Maybe you're near gas stations, or maybe you're near other areas that have particular risk. And so it's about the standard is all about evaluating risk and then applying measures systematically to calculate a reduced risk. The IEC standard applies the use of materials, which are covered under 62561, separate categories. I just want to draw attention that it does pay attention to isolated lightning protection systems. So lightning risk starts with the analysis of your application. Are you a hospital full of babies and liquid oxygen? Are you a charging station with lots of humans nearby? And you calculate your risk if you don't apply protection, and you apply protection to reduce that risk below a tolerable threshold. So there's industry standard tolerable risk reference levels. And for instance, human safety is 1 in 100,000. So if your risk is too high, you reduce it below 1 in 100,000. And that's the whole point of this chart at the bottom. Is it's basically giving you the blue threshold and the red out of control risk, and then the green under control. Now you've reduced the risk below the thresholds. And so these principles can be applied to any number of type applications. You look at the building structures, the areas that are involved, the size of the area, the number of strikes per year for references from places like Vaisala. And you can overlay this onto your application of a charging type station environment. You can see the collection area of direct and indirect strikes. You get your risk before you do protection measures, and then you get your risk with protection measures. It's a little hard to read on my slide, but if you apply the principles of lightning protection from the pillars of lightning, you can reduce the risk. And this is just a slide I like to use to describe the lightning protection mathematical parameters. So lightning is charge moving through the atmosphere. It has a charge content. It has specific energy. It has a peak current that's provoked by these charge moving through the atmosphere. It has essentially a timestamp, a fingerprint of what the lightning peak rise time and decay time looks like. And the IEC standard gives you the mathematical principles to use for calculations. Is the lightning surge protection adequate to withstand the risk category? So in our calculation methods, we assign a level of risk that we want to control. And if you have high risk, you put more measures of protection. And what it might look like is more lightning rods and more grounding and more surge protection devices. So the worst case scenario is that you've got a very high lightning current up to 200 kA and a very low lightning current, 3 kA, which defines a small radius of the rolling sphere. The more lenient type 3 level, LPL level 3, which is much more in line with an NFPA standard, is defined as 100 kA of lightning current. So your connectors have to be able to withstand the lightning current. And the 10 kA lower level defines a more relaxed radius rolling sphere, a larger radius, a little bit bigger spacing between lightning rods, essentially, is what it allows. And that level of risk is suitable for what's considered a normal environment without a lot of extra things that will explode. In the IEC methods, it tells you you can use a rolling sphere, you can use protection angles, you can use wire mesh, which is very similar to like an air terminal placement type method from NFPA. And the point is, what you're seeing is that the standards are aligned. They use the same principles. The rolling sphere radius for LPL3 is the same radius for the typical risk of NFPA 780. But what's important to notice is that the standards are aligned with subtle differences. And the UL 96, as I'm pointing out here, is similar to this LPL3. And the way this protection angle works is that the taller the structure, the more relaxed the angle can be that generates protection area under that mast. And this is what you might see in an isolated lightning protection system, where there's a mast out in the switch yard or at a gas and oil plant where they're isolating the lightning away from the victim. This is a nice illustration representing that difference in the rolling sphere. So you can picture in your mind's eye a high risk environment, outdoor, charging station, no coverage around. You're out in the middle of a parking lot. You actually have a high risk that if you're charging right at those moments, the lightning might hit the light poles nearby, in which case you have quite a high risk of touch step voltage around the charge station. And the equipment and the human factor are all subject to much higher stress voltage. And that stress makes its way into the electrical wiring, which is the reason you need more or less surge protection. So a smaller radius is higher risk. A more gentle, a bigger radius, a bigger rolling sphere means that you essentially don't get into all the smaller nooks and crannies, and you would essentially have fewer lightning rods engaged at the site. But there's an important aspect of grounding that goes along with the lightning protection system. So if you have a higher risk, you need more grounding buried in the earth to essentially dissipate the lightning energy. And a standard, what might look like a standard 5-meter rod, call it a 20-foot rod, a standard 20-foot rod is not enough if you have high risk. So what you'll find in a chart like this below, what you really see here is this 5-meter, this is the length of the rod of the buried earth conductor, and this is the risk based on the soil resistivity. You have high, if you have really great moist, high conductivity soil, then you have a derating factor. But as you increase the risk that you evaluate, remember, you start with risk evaluation. If you increase the risk, you need more depth of earth rod, not just to get your 20 ohms or your 5 ohms or whatever the standard might say for NFPA 780 or National Electric Code. It might say, you should have a 25 ohm connection and you should put in a 20-foot earth rod. If you have a higher risk, it's not enough. You need more earth rod. That's to control the risk. And we like to really look at this at a detailed scientific method where we can establish the soil models for the layers that are out there in these types of sites. Very difficult to measure when you're at a existing legacy type parking lot, But if you have access to the actual soil model data, you can build up what are very effective earthing calculations. And Dane has done a lot of work with understanding the soil model at a site and then applying that to the actual touch step voltages that you're going to see at different types of sites. And here's some modeling that we've done at, for instance, solar fields. We have done similar modeling for vehicle charging station, and you get a very typical result. If you don't bond and ground the apparatus, you will have what essentially you can call them lightning hotspots, where there's extremely high touch step voltage. And that's what you see in a chart like this. The depiction of the colors and the height of that spike is the touch step voltage around the region where you might inject lightning energy or where you might have insufficient grounding and bonding across the charge station site. So here we're showing a spike with a very high voltage gradient. And what that means is you're getting something like 20,000 volts per meter across your feet or up to the spot you're touching your vehicle around those hotspots. And if the light pole, now picture that light pole out in the middle of a parking lot. If that light pole is not grounded correctly, if the charging station infrastructure is not grounded adequately, you'll have extremely high hotspots. And the idea behind grounding and bonding is to level it out, smooth it out, so it dissipates more evenly, and you have equipotential grounding, and really the best control of the risk. So now we're back to the whole risk evaluation. If you evaluate using methods like this, you can see that you might exceed the touch step voltage for adequate and safe application across a charging station. This slide is just a quick introduction to a couple of functions of how surge gets into your equipment in the first place. So you're looking at something like a charge station. There's direct strikes where you have extremely high lightning energy injected directly onto the infrastructure. Then there's indirect strikes that might be 20, 50, 100 feet away, a mile away, where it's striking the ground and it's like an indirect type of a strike. This 8 by 20 and these 10 by 350, these are the industry standard type waveforms described by IEC, and they give you a definition for a direct lightning stroke and an indirect lightning strike, which is this 8 by 20. This is what you see often applied to electrical standards like UL 1449 and the IEC 305 type suggested surge levels. And this is a 8 microsecond rise time with a 20 microsecond decay. That's much shorter, less energy content, less stress on the electrical systems. And then you also have any manner of surges that are induced from transients on the electrical grid, that from switching between different power sources. You could have switching transients from solar panels, battery storage. You could have switching transients from the high tension grid from your power service providers. It could be shorts on transformers, earth faults, tripping of fuses, nuisance trips that might be caused by a nearby strike that causes the battery storage or the other switching systems to trip out. You might have ground fault, things that look like that hotspot from lightning strike that actually has an influence like a ground fault trip. So there's all sorts of tripping sources that can also directly induce electrical surge into your charging station wiring systems. This is a nice slide that some research that Dane has conducted to compare the military standards with the IEC standards to show the equivalency of lightning intensity. And the point being is that the NFPA standard really doesn't give you any guidance for lightning intensity. And so this at least gives us the input for things like those electrical models where we're trying to model the lightning environment. You need a lightning strike injected into the system. You have to have the parameters. And what we find is that we can use calculus to show that we're actually very similar to the mill standard energy content, peak current ratings, the actual amp squared second, the actual lightning strike parameters that help us understand what's actually in the environment. And when we look at data from companies such as Vaisala, you can actually look at the distribution of lightning strikes that they measure, and they do see lots of strokes that have this content rating in the 10 KAs. That's very common. And then you see some strikes, these Wrath of God strikes, that are up there above 50 KA or above 100 KA. And that gives me some sort of a nice parallel with the way that the probability of a strike might occur. Much like what's in the IEC chart here to the lower right, there are some, the 99th percentile, just a few percent of the time, but there's some strikes that are way up high, way Wrath of God type energy content. And so when we can look at this type of data, it's nice to see that there's a good commonality between the standards and how the calculations apply. So this is a nice example of what a site might look like out in the real world, where you've got a structure and then what the rolling sphere looks like around that structure, where the things like smokestacks or things like water towers, they all have an influence. And this is that illustration of that rolling sphere across a more complicated type site. Charging stations can be any manner of size. You'll have much more complex structures coming together with 10, 20, 30 charge stations in a row. So you're taking up a lot of real estate. You have a lot of parking space type real estate. So these stations become very big and complicated, and you'll have much more of a description that looks a little bit more like these types of large sites. And the actual installation of the lightning protection air terminals might look a little bit more like these types of sketches here. These are just examples of the air terminal and how to put an air terminal onto existing structures that are maybe around your site. This is a really important aspect of lightning protection. It's the grounding. It's how well is the equipment connected into the earth grid. And so what you see is a collection of measurements of the pigtail loop with these types of instruments, the clamp-on meter, that gives you an indication of a above grade and buried connection. And what I mean by that is the entire lightning protection system depends on being very thoroughly connected into the earth. So up at the top here, we see a structure, and you go around the perimeter of the structure and you see very low impedance measurements. And this tells us that it's connected above grade and probably a massively connected steel structure. Not a big surprise that the corners of the structure are connected above the soil, but it's very reassuring to see that it's a low connection below grade as well. And so what we'll look for in these types of measurements are types of readings that are very far away from the other readings. In other words, higher magnitude or much higher readings. So if everything around the structure is 1/10 of an ohm and you get a reading that's 100 ohms, it's not in the same even ballpark of a connection. Something is different. It's not connected as it should be. And it gives us a way to diagnose and evaluate a site and make sure that it's actually properly connected above grade and below grade. And this translates into what might be hotspots in things like that soil modeling and the modeling at a site. So this entire site could be converted into a finite element mesh, and we can evaluate the hotspots for a site based on what we see in these types of measurements and in the soil evaluation. So the application of surge protection is pretty straightforward. If you have more current, you might need more surge protection. And I say that might because if your service entrance is rated for anything less than 200,000 amps, if your actual power coming from the substation is and from the transformer pole is limited to less than 200,000 amps, then a well-designed surge protection device does not need to change based on the load. If it's 1,000 amps, it's the same device as if it's 100 amps. The surge protection is rated by voltage and available fault current. Those are the ratings that really make the biggest difference. In the horse race of surge protection, bigger is better, but that's not for the case of what's needed. Bigger might be great if you want it to last longer in the application, but it's not how it's rated by the electrical principles. And so this is a sketch with the variable speed drive you can overlay this with a bigger or larger charging infrastructure. If you're talking about something so many kilowatts, then you're talking about so many amps of current. If it's a bigger charge station, you don't necessarily need bigger surge protection devices at those charge poles. As I pointed out, the rating that you're looking for is the voltage that it can be applied on, the maximum continuous voltage, and the short circuit current rating. So we use a selector, very simple. You plug in the voltage of your application, and it tells you which types of SPDs could work for that application. So for instance, 120 volt or a 480 volt surge protector gives you its core ratings so that you can properly select a safe device. There's a lot going on in a sketch like this, and I want to make sure that we superimpose this correctly into what we might call the charge world. You have maybe a central station, maybe a main convenience store or a hotel charge power room, and it's feeding power and data out to a charge pole. This would be something that might look like the charge station 100 yards away from the other equipment. They could be under completely separate ground fields. And so when we're sending data across those connections, your low voltage shielding there's really a lot to pay attention to. So on one end of a data cable, we will bond the shield on one end. Here we're showing it bonded at the what we're calling MEB1, Master Ground Bar 1, at maybe the central office, the headquarter office of a charge field site. Now superimpose a charge station that's out in the parking lot, and you're sending a data cable out there, much like a RJ45 or maybe a 4 to 20 milliamp data cable. And at the other end of that cable, the shield is not bonded. You notice that there is not a green connection. That is a gas discharge tube type element for the shield. And what that does, it's an extra measure of surge protection on the shield at that remote end. And the purpose is to control the voltage on that open shield. So much like the pressure relief valve on your water tank, your water heater, if the water pressure, the voltage gets too high, it can release that momentarily and it can short out through the gas tube. Control that voltage at the shield. And we've seen a lot of applications because the ground is different between those structures. And if it's completely separate ground fields, that shield can rise significantly. You can have a lot of voltage buildup across the shield at that remote end, which then injects somewhere else. It finds a path, and you don't want it to go into your equipment. You don't want it into the victim. So not only do you apply surge protection, the yellow surge protection device at your equipment, you put a shield protector in as well. And here I just show a schematic of something where you can see that shield is connected through the gas tube. This is an interesting sketch that shows similar types of problems with the connection of the surge protector, common mode versus differential. And the sketch to the left is what's called common mode, where we expect most of the surge energy to be from line to ground. In other words, the two pairs, the wire pair, are twisted together, and they're not really developing a lot of, we're not as worried about the voltage across the pair. We're worried about the voltage from ground. For instance, when there's a grounded type system, you can have, now it gives you a way to control the voltage to ground and divert the energy to ground. It's really, remember, it's about controlling voltage and diverting energy. And this gives you a way to divert the energy to ground through the SPD device. If your device is floating, there's really no ground to reference anyway. Now you want to apply the most protection differential across the lines. And what that means is it's a system where it goes out to a plastic box on a pole. There's really nothing that's referencing ground at a camera or some plastic device, maybe. That's something that you might see. Or maybe some sort of card reader. But if your data collection on your charge pole is ungrounded, this might be a better solution for you, because you're protecting between the wires and you're controlling the voltage and trying to divert the current back. Remember, in the earth system, you're diverting the current to the earth because it's optimum. So these are just some really good ways to apply surge protection on the data collection circuits. Within Dane, we have a very unique device that actually measures the life of the surge protector and tells you if the surge protector has failed. If the protector has failed, we can give you a visual and an electrical on-off switch annunciation of the status of the protector. This is another layer of control and maintenance and information gathering for your site. We've talked to a lot of customers, and they want to understand the uptime at their charge station. They want to know if they have to come out and replace stuff. They carry spares of everything on their truck. They probably have a complete spare charge pole that they're ready to install and troubleshoot and get that charge station running. And this type of a device can give you information for the deployment of your crew to go out and repair a charge site, so that you are coming out with the most information. You know what's failed. You know the surge protector has failed, or maybe not. You'll know the surge protector hasn't failed. If you have no indication of failure, but something else is broken, that gives you a level of troubleshooting before you even deploy out to go start to try to do repairs at a site. Here's a type of device that might be on the data collected side of an exposed half-inch NPT pipe thread apparatus. Maybe there's a light pole that has this type of access where you can get a surge protector directly at a camera or another type of device. We have a wide range of surge protection devices for power over Ethernet, which is a very common protocol back and forth between a charge pole bringing 420 Ethernet data back to a switch where the main data is collected. And so we have indoor rated and outdoor rated type surge protection devices that would go directly at those applications in line to provide protection of the Ethernet port on the charge pole, but also at the network switch inside that's gathering that data for telemetry. And these are just a couple of quick block diagrams taking that principle, the entire lightning protection principle, rolling sphere protection under the lightning protection coverage of these air terminals. But notice that some of the vehicles may not be under a lightning protection coverage. That's back to the control of risk. The other thing to understand here is remember, it's the pillars of protection. We're looking at all of the aspects. Here you're seeing a nice block diagram connecting the ground systems at these charge poles so that you don't have these hotspots or these unconnected floating ground areas. And then the surge protection might look like some manner of device where you have all the data protected and all of the power protected. This is a couple of sketches of what you see in the real world and how that might look in a protected environment. So here you've got charge stations out in the middle of a parking lot. And where do they connect? How is it bonded? Is there true surge protection applied at both ends of the power delivery system and the data collection? So these are just images in your mind that you can overlay and look at a photograph and evaluate, does this really look like it has a ground properly applied around that charge pole? So here you've got a charge pole next to a hotel, and it's tapping off power from a electrical control box. And so in your mind's eye, can you see the aspects of the pillars of protection being applied? Is there real bonding and grounding occurring in a situation like this? Here's something that might look like a fleet charge station, and you have a nice awning over top of you that's great for sun and rain. But if this gets struck by lightning, has this structure been properly protected? Does it actually have air terminals applied? Where will the lightning currents likely go if this structure is struck by lightning? Is it going to be injected into the grounding directly around the perimeter of this structure, which will influence these charge piles and the vehicle and the human operator standing around it? So here's an overlay of that same sort of principle. Is the air terminal properly applied to the awning? Is there a down conductor? Does it go into a grounding system that's buried like a mesh? Here you see the mesh buried underneath these parking stations so that you have the best control of the risk of lightning. And you're controlling the charge station, but you're also controlling the risk to the vehicle and the occupant. Here's a few illustrations and some photographs of what that isolated type system will look like. So what's important here is that the lightning might strike this mast, but the conductor is not bonded to the structure, and it's only introduced directly into the earth. So you're not energizing the structure. You're dissipating lightning into the earth, directly into the earth, and not trying to couple on and spark into the equipment around it. And so what you're looking for are the actual application of surge protection devices in these cabinets and in the charge pile itself, the actual apparatus which connects. That's the closest connection to the vehicle. If you want to protect the vehicle, you want to be sure that the surge protector is as close to the vehicle as possible. And that's going to be right at the charge pole. Two examples of what to watch out for. Now, of course, this is a different environment. This is oil and gas related, but remember, we're talking about lightning. It's going to find ways to induce arcs and sparks. And what we try to do is create an environment at a holistic level. Start with the lightning protection, the earthing, the down conductor systems. Create an environment that actually has a protected zone around the victim. And in this case, you could look at it as a charge station. You could look at it as oil and gas, or maybe you're a very critical mission like a Launch Pad Complex 40, where you can see the isolated mast around it. Although it's very difficult to see, you can't really see it. There's guy wires and catenary systems around this whole system. And that's engineered to provide the most safe environment for the victim. You've got a rocket full of a very high valuable asset full of rocket fuel, highly explosive, very high risk environment. You want the maximum control of the risk, which is isolated lightning protection systems with surge protection applied to as much of the structure and vehicle as possible. Thank you for participating with our session today. If you have more questions, visit us on social media, visit daneusa.com, contact my colleague Ben Ellis, and remember that we have a Florida Professional Board of Engineering license number and file for the session today. This concludes the recorded portion of our content today. I'd like to ask Lisa to go ahead and discontinue recording.